Yeah, all right. So welcome everybody. So today is my pleasure to have this thematic afternoon on machine learning and dynamical systems with application to finance. So we have two speakers, Lorenc Kapllani and Tatiana. And yeah, first speaker will be talking about deep learning and uncertainty quantification for solving high-dimensional backward stochastic differential equations. Yeah, thank you.
Thank you, Professor Hamzi. So welcome everyone. Today I'm going to talk about deep learning for BSDEs, which are mostly in terms of the application to finance and their uncertainty quantification. So this talk is going to be actually in two parts. In the first part, I'm going to present some new algorithm that we have studied for solving high-dimensional BSDEs, and which is the work from me and my PhD supervisor, Lorenc. And the other part of the talk is going to be about the uncertainty quantification, which is a joint work with Dr. Matthias Rothman. Okay, so just a small overview. Yeah, at the beginning, I will discuss a little bit about motivation, why using deep learning in BSDEs, and the problem that we are considering, some important formula that is important for the deep learning approach. And then moreover, I will discuss one of the pioneer works, which I name here the SDNN approach, which stands for Stacked Deep Neural Networks. And then the LSTM approach that we have studied. And moreover, I will present some numerical results which show the advantage of this new method compared to the pioneer work from Professor Winan E. Okay, so yeah, now about the motivation. Yeah, the main motivation is that we want to solve very high dimensional problems in, especially with the applications in finance. However, we have a lot of faced with a lot of challenges, and the most one is the curse of dimensionality. And so now we need to think about which would be the right equations so we can model this kind of problems, and which would be the right tools for solving these equations. And the most important, of course, to get the results in a very reasonable computation time. And the way out from all of these challenges is to consider the equations to be the backward stochastic differential equations, and to solve this kind of equations with deep learning. And another very important advantage of these equations is that they does not only present let's say perfect market models, but also imperfections, such as when we also consider stochastic volatility or local volatility or market imperfections and so on. Moreover, this kind of equations, they present a probabilistic representation of the problem. And this offers the possibility that we can model that, or we can formulate them as deep learning problems. And until nowadays, this is the only way, one of the only ways how to consider these very high dimensions. And we say like 100 and more. So the form of these equations is as follows. It's present from two different stochastic differential equations. The first one is the forward process. And for example, in terms of the option pricing, it is the dynamics of the stock. And the second part is the backward stochastic differential equation, where there are two processes, Y and Z. And there is also Xi, which is the terminal condition. In case of the option pricing, this is like the payoff. And F is the driver function. And moreover, the relation with the pricing and hedging of option, it has been done since 1997 from Nicole El-Karoui. And yeah, so Y represents the value of the option and Z represents the hedging strategy. So an important formula for this kind of equations is the one from the Feynman-Katz, which gives the relation between the partial differential equations and the BSDEs. And if you, for example, this is as follows: if you consider that this YT is a function of time and the space, and the ZT as a diffusion multiplied with the gradient of this solution, then the solution of the BSDE is in fact the solution of the backward in time parabolic PDE, which is given in 2. And under regularity conditions, this PDE2 has a unique solution UTX, and the triple XT-YT-ZT is the unique solution of the forward backward SDE that I showed in the previous slide. Okay, so now, of course, we need to do a time discretization for the equations that we have. And for this, we consider time discretization. And then if we follow the notation that I've written here, then from an interval ti to ti plus 1, we can present the backward SDE as follows. I mean, I'm not writing anything about the forward SDE because these one are very well known, their discretization. And for example, even though the calculations, the classical calculations of the BSDEs take part backward, we can also formulate them in a forward way, because this actually helps us to formulate them in a deep learning framework. And the Euler forward time discretization is as follows. And I am denoting the right-hand side with a capital F, because I will put it again below. So it's just the Euler discretization, this capital F, for the process Y. And now I'm just going to present the algorithms that that solve this kind of equations. The main this is the algorithm, the pioneer work, as I told you, for Professor Vinan E. And this is as follows. So SDNN, as I told you, stands for stacked deep neural networks. And the idea is as follows. So we start at the time t0. Of course, this is what we are interested in. This is the solution that we are interested in, which means in terms of option pricing, we want to know the fair price of the option today. And of course, it's a hedging strategy and so on, which we directly get from the BSDE. And so the idea here is that we start with some initial parameters for this Y0 and Z0. And what we do is that for other times until before the maturity, we use a deep neural network to approximate the function Zi. And for Feynman cuts, we know that this is like a function of this x, and x here is the value of the forward process at each time step. And this one we can easily calculate by using some Euler-Maruyama method or Milstein and so on. And then we calculate the Z with the neural network, and then we calculate Y by using the Euler discretization of the BSDE. And moreover, when we go up to maturity, then we calculate again the Y by using the Euler discretization. And what we know from the problem is that we know the payoff. So this function that I wrote here, phi of as a function of xn. Xn is the value of the forward process at the end. And this one we know. And so now we want to create this loss, and this loss, which is the expectation of this difference squared, and this is what we actually try to match. So in a sense, we are learning the initial parameters, and also together with the value of the Z at each time step. And moreover, we are from these values, then we approximate the value of the Y by using the Euler discretization. And then by using all of this, by going forward until the end, then we try to match what we know, which is the payoff. And then by using gradient descent methods, for example, add the method, then we can minimize this loss and try to find a good estimate of the solution. And so for example, this is how this architecture looks like. So as you can see at the beginning, we start with some value of Y0 and Z0. And then this F0 is just that we calculate all this the information that we take, so we can calculate Y1. And then by using the X1, then by using a neural network, we can calculate Z1, and so on. We go forward until the very end. There we can have a loss, and then we can optimize and update these parameters until we get a good estimate. And this method is very good, and it can provide very good results in high dimensions, 100 or even more. But however, it has an advantage, and this, it has a disadvantage. And this disadvantage is related with the fact that if you have a very long terminal time, which means like the maturity of the option, like if it is 2 years, for example, or when the driver function, which models these equations, is very complex, then this method fails because it will not be able to match the terminal condition. And therefore we'll get stuck in some poor local minima, or will actually diverge. And since we have this kind of disadvantage, then we have this motivating question that how would we do this thing? And the motivation would be that we need to give more information to the loss function. So in a sense, since we have information only at the end, we need to try to give information even in the other time steps. So the idea in this case would be as follows. So instead of using the discretization of the BSD for the Y process as an update to the Y process, then we use it as an information for the loss function. So this means that even Y, and for example, we approximate Y now not with the Euler discretization, but with a neural network, and we can approximate Z by using the automatic differentiation, because we can get, we know from the Feynman-Katz formula that the Z is the diffusion times the derivative of our solution with respect to the X, which is the forward process. And therefore, now I will also show you a bit later in the next slide the algorithm, and then I will show you also the architecture to understand it better. And but the main idea is like this. And then which kind of network architecture would fit better this kind of loss function? Well, actually, recurrent neural networks would actually make more sense here, because now we have in every time step we have a local loss function, and so this would be very nice for the recurrent neural networks, because this also inherit the information from the previous layer to the next layer, which is same as the BSDs that are adapted to the filtration. And another nice thing from this would be that now we have one neural network. And in some other work that we have done, we found out that the previous approach, since it has multiple neural networks, it actually does not give very smooth results for the Z process, because you have too many neural networks. However, when you use only one network, you have smoother results for this process. And the algorithm actually looks like this. So again, we start at the beginning with some initial guess of Y0 and Z0, but now from time 1 to time n, for example, we use, in terms of the recurrent neural network, we use LSTM, because to avoid the vanishing and exploding gradient problem, and not to get confused with the classical LSTM. So we are just not only using the LSTM here, we are using the LSTM, which also which has a loss, and in this, inside this loss function, as you can see down here, this is this has inside all the information for the that comes from the discretization of the BSD. So it's not just only the LSTM applied here, but it's the combination of the LSTM and the BSD, which is here in the loss. So for at every time step, we use an LSTM to approximate the Y, and then we approximate Z by using the automatic differentiation. And then we gather all of this information at each time step now, together also with the information that we have at the end, and we consider this loss function. And then, of course, we try to optimize this loss here. In other words, this is just like this. So we just consider a network which at each time step gives us the output for the Y process, and the Z we calculate with the automatic differentiation. But the loss function at each time step tries to match the dynamics of the BSD, and therefore that's why it is going to converge to the exact solution. And so now the architecture looks a little bit different, because now we have multiple losses at each time step. And as you can see, we have the same, of course, the same network at each time step. And at every time step, we have the output Y. And then from this one, we can calculate the Z from the Feynman-Katz formula. And then we have the loss at each time step until the very end. Okay, so before I continue, is there any question until now? Okay, so there's not any question, then I will just continue now with some numerical results. So to show the advantages of this new method, so we consider this very complicated forward-backward SDE. And you can see here, which also actually has an analytical solution. And yeah, it's important for us to see that if actually the results are convergent or no. And some simulation information is that we run these codes in TensorFlow. in Google Colab, and we considered 10 independent runs and take their average as an estimate for the solution. And the hyperparameters that we consider for this example is that a learning rate of 1e-2, a batch size of 64. For the SDNN approach, we consider 2 hidden layers, and the number of neurons is 10 plus d when d is the dimension, and we consider 1000 optimization steps. And in the following tables that I will show, these are some notations just to not get confused. And yeah, so here, so we consider for d is equal 1, the exact solution for maturity 2 and the other parameters is as follows. And in the first table, you see the results for the Y process at time 0. So this is the so in terms of the option, this would be the option price at time 0. In the left-hand side of the slash, I just consider the values for the SDNN approach and the other side for the LSTM approach. And considering increasing time discretization N. So we can see that the SDNN approach diverges. So you can see these non-values. And the other approach is working very well. And you can see also in terms of the error. In terms of the computation time, this other approach is a little bit more time consuming because we have a loss function which is much more complicated. And moreover, we also considered for 100 dimensions, but with capital T is equal 1 here. And we can see that the results for the LSTM approach are much better. So you can also see here in the third column the error, which is with the increase of the time discretization, it is also the error is decreasing. But in case of SDNN approach, it's a little bit more, not that much stable. So sometimes it's also increasing. And so these are the results for the Y process. And then we have the results for the Z process. Also, the results are also good even here. As I told you, in terms of a computation time, yeah, this is a little bit more time consuming, but when you increase the number of time steps, maybe 64, maybe 1028 and so on, then the computation time may be almost the same, because in the SDNN approach, we have a different neural network to each time step. So there the number of parameters will be much bigger, but in case of the LSTM, the only constraint in terms of the time is due to a very complicated loss function. So to conclude for this part, we can see that we have convergent results for this new algorithm for when we have very complex problems or even long terminal time. Moreover, we consider another example. This is an example from the finance, option pricing with default risk. And the corresponding forward-backward SD is given as follows, where we can see here that the driver function is quite complicated. And yeah, so just to save time, I'm not going to all of these parameters here. So of course, this one does not have an analytical solution, but the approximate solution is given from the multi-level Picard approach, which is 57.3. And then we apply both the approaches, SDNN approach and the LSTM approach. In this case, here we consider a little bit a bigger learning rate, because yeah, here this is a little bit more complicated to get to converge to the exact solution, which is even higher in value, and also increased a little bit the optimization steps to 4000. And as we can see from here, even here, the LSTM approach works very well, even for complex option pricing problems. So yeah, so this is the first part of the talk, which was about this new algorithm that we developed. And now I'm going to talk about the second part, which is, as I told you, joint work with Dr. Matthias Rothman. And this is about uncertainty quantification for deep learning BSD approaches. So in this part, I'm again a little bit the motivation of why we need uncertainty quantification in this kind of cases, and the approach that we are considering, and some results that we have. So this is still working. This work is still ongoing. And yeah, these results maybe sometimes may not be perfect, but we are always just learning as much as possible until we get our perfect results. And yeah, so I will just also show the results here by first considering the Black-Scholes BSDE, because here we have the exact solution and we can compare the results from our uncertainty quantification model. And then also with another example, the option pricing with different interest rates, where we don't have the exact solution, and to see if, of course, because there it's more important to have the uncertainty, since we don't know the exact solution, and to see how this our approach works even in that case. And then to conclude this this talk. Okay, so motivation is because, of course, we don't know the solution, and another thing is that the loss that we get from these deep learning approaches does not say anything to us about the uncertainty in this kind, in the approximate solution that we get. So therefore, we need to do uncertainty quantification. Moreover, we also receive, from when we solve this kind of problem, we just receive a point estimate of the solution, and we don't know anything about the uncertainty. So yeah, of course, still we definitely need to see to check the uncertainty in this kind of problems. And in terms of the finance, yeah, we by having the uncertainty related to different problems, we can also do risk management, which is very important to minimize the monetary loss in this area. So the idea for uncertainty quantification is as follows. So the idea is that we want to consider perturbing the loss function. As I showed you before, the loss function is the function of the terminal condition. And we want to, by perturbing this this loss function, then we want to construct some sensitivity indicators, and these are taken by consider the gradient of the perturbed loss, and we want to register what is the change from this perturbation that is done to our network architecture after a single step of backpropagation. And by gathering all of this information, then we want to estimate this change in the solution, as I showed in equation 5, from where y0 hat is the estimated solution for the perturbed loss, for the perturbed terminal condition, and the y0 for the unperturbed terminal condition. And these sensitivity indicators are calculated as in4, and we denote them by delta. Delta I here are the gradients with respect to this perturbed loss, with respect to these values of the y, which is the output from this from the network. And we also register, since we can easily register also the gradients with respect to all the weights of the network, all these weights theta. And after we gather all of these sensitivity indicators, then we apply another model, for example, a linear model or a nonlinear model, depending on how the relationship is, to quantify this uncertainty. And but now the question that arises is how to apply this perturbation to the terminal condition. And this terminal condition, as you know, is a function of the forward SDE at the end. And moreover, the forward SDE is also as a function of its initialization x0, also the drift term mu and the diffusion term sigma. So which should we perturb from all of these parameters? Well, in finance, we know that the volatility is a parameter which cannot be observed in the market, and therefore the parameter which is used is the implied volatility. And this is one of the parameters that this is the parameter that actually inherits uncertainty in option pricing. So therefore, definitely the answer is that we should perturb volatility. So we can apply this method here, which was developed from Oberdick, Matthias Rothman, and Hanno Gottschalk in 2018. Okay, and the procedure would be as follows. So the idea now is that, of course, we need to gather data so we can create this model, and therefore we need to solve multiple problems. And therefore we generate a domain of values and say M values. And then we should resolve each of these problems. For example, we consider to use the SDNN approach, which is a very well-known deep learning approach in this area. And then what we do is that we apply the perturbation and we evaluate the indicators given from equation 4 up here. And also we estimate this change in solution given by 5. And finally, after we have gathered all of these data, then we can learn an uncertainty quantification model. So as a motivating example, we consider the Black-Scholes forward-backward SDE, which is given as follows, which of course has an analytical solution and is given from the following equation. And yeah, so here the payoff, here the thermal condition is given from the payoff of a call option ST minus K. But yeah, we can also consider put and so on. So actually, first we need to see if there is uncertainty from this when we solve this kind of equations via deep learning. And to show this thing, the uncertainty that is coming from this stochastic gradient descent, what we did is that we fixed the parameters, the problem parameters T, interest rate, and so on. And so I don't know if I should answer the question, but okay, I think I will continue until the end, and then we can have the question and answer session. So we have this all these parameters, and then what we do is that to see this uncertainty coming from the stochastic gradient, we fix the seed for the data, for our input data, which is from the forward process, and also the initialization of our solution. We just keep it to 0, 0. And then we consider a different seed only for the initialization of the network weights. And then we see in terms, as a function of the optimization steps, we plot the error and the loss. Sorry. And you can see here from this table, I hope you can read the labels. So in the x-axis, you have the iterations, the optimization steps. And in the y-axis here, we have the error. And we have here 100 different runs, which are with different colors. And as you can see, there is high uncertainty in the model. So every run somehow has quite a lot of, has a difference with the other runs. And yeah, this is the plotting for the loss function. And as we can see, the loss function for every run is actually decreasing. But even though it's decreasing, we can see up here that the error fluctuates a little bit. And yeah, as this loss function does not give us any information. That's why we really need to do to consider some uncertainty quantification model. And moreover, in this table, I also show that the correlation between the loss and the error. Here, the loss is just for the Y process. We can also do it for the Z, but just I did only for the Y here. And we can see that there is not any clear correlation between the loss and the error, which is still gives our more importance to consider the uncertainty quantification. So yeah, as I told you, that now our approach was to consider this perturbation of the terminal condition, and as I told you, the perturbation would be it makes sense in case of finance to consider to perturb the implied volatility, which is an estimated value. And since it's estimated value, it also contains some confidence interval. So now the questions that arises here is that whether we should make this perturbation with a constant standard deviation, for example, with some with some Gaussian noise with standard deviation 0.1, or we should actually consider a different, we should consider that this implied volatility has a non-fixed confidence interval, and to consider different perturbation with a different standard deviation after each simulations that we do. And moreover, we also want to see whether our UQ model can actually generalize. With generalized, I mean that if we can create an uncertainty quantification model that can give us the uncertainty quantification for a call or a put option for any kind of parameter, sigma, so the volatility, the maturity, the interest rate, or the stock price, initial stock price. And to answer these questions and to understand more and more in this area, what we did is that we considered these 4 different approaches. So in this table, you can see that in the left-hand side, this part represents the perturbation. So I will try to be very clear about this part because it may also be very confusing. I hope it will be not. This kind of approaches have two directions. So the first direction is about the perturbations that we apply to the volatility, to sigma. So as I told you, whether we consider a fixed perturbation, let's say 0.1, or we consider a different, we consider a fixed standard deviation for the perturbation 0.1, or we consider a different standard deviation, which is sampled, let's say, from some chi-squared distribution with 1 degree freedom, and we consider the square root of this with this factor here, so that we can have it all these values to be generated around 0.1. And then to answer the question related to the part of whether it can generalize or no. So in these four approaches, as I have presented in this table, the first part represents whether the perturbation is with a fixed standard deviation or with a non-fixed standard deviation, which is here I wrote as stochastic. And the second part in this approach represents whether we vary only the standard deviation. So we solve a lot of problems where we consider different standard deviations, but we fix all the other parameters like the maturity, interest rate, and so on. And the other approach is other approaches are whether we also vary this parameter. So will this also give us much more information for our UQ model or no? And therefore we have all these four models. So I just want to repeat again that the first part represents the perturbation that we apply, whether it is fixed or it is stochastic. And the second one represents which are the parameters that are varied in this case. So it's whether it is only sigma or all the other parameters. And here I also present how these parameters are varied. And for example, we vary the sigma to be, so we try to vary all the parameters to be within a practical range. For example, the volatility from 0.01 to 0.4, the maturity uniform distributed from 1/12, from 1 month up to 2 years, the interest rate from 0.001 to 0.1. And then we also consider to have in and out of the money options by considering to sample this S0 uniformly within this range here. And for example, here in our results, we considered strike price 100. We consider, so this delta is not the indicators, but this is a mistake from me. It should be another naming. This is just the dividend rate for the stock, but for simplicity, we consider 0, and mu is the mean return, which is 0.05. And if we don't vary the parameters, then we fix them to the capital T 0.33 and the others. And for the perturbation of sigma, as you can see, we considered for the fixed case, we considered the standard deviation of 0.1. And of course, we should not have a negative volatility. So we consider this maximum with respect to 0.001. And if we have a stochastic perturbation for the volatility, then we consider sampling from a chi-square distribution. And for the asserted quantification, we considered 3 models to consider whether there is linearity or non-linearity. So the linear regression, we consider the lasso and the XGBoost. And for the moreover, for training, testing, and or validation samples, we considered for the time discretization n is equal to 16. And we considered to train this UQ model like 1,600 samples and 200 for testing and 100 for validation. Moreover, for performance metrics in this model, we used R squared and RMSE. And we also, I'm going to show some analysis related to feature importance. So I want to show that this gradient metrics actually give a lot of information to the UQ model. And to compare to further compare that the UQ model performs much better with this gradient information. We also consider some baseline models, and the baseline models are just only the parameters that we know from the problem, and not this gradient metrics. And okay, so these are very big tables. I will try to interpret them as easy as possible. So here we have the 4 different models, and we considered as a baseline model, we have the baseline linear and XGBoost. And for this one, we have when we have the first model, which has a fixed perturbation, and we vary only sigma. Then, as in the baseline model, the input that we can give, that we have from the problem, is the sigma that we vary, and also the absolute value of the difference of the loss. L is the loss at the end of the optimization process, and L0 is L0 hat is the loss that we consider for the perturbed terminal condition. And for the other models, yeah, we also add all the other information that we have. For example, in case of when we have the fixed perturbation and we have other elements that we are other terms that we are varying, like sigma, T, R, and S0. So here we also add this in the baseline models. So as I told you, the baseline models are only without this gradient information. So it's the first line here and the second line here. And the other 3 models is when we also add this gradient information. And the first part here represents the for the training sample, and the other one is for the testing sample. And then we have the RMSE and so on. So as we can see from all of this table here, we can see here that the best model that performs better is the XGBoost. So we can see also when we fix also only sigma, or we also keep sigma as stochastic, and so the perturbation is stochastic. And so as you can see here is the works better from all the others. In the second table, so since we are working with a Black-Scholes equation, for the Black-Scholes we have the exact solution. So we can calculate this exact change in the solutions due to this perturbation. And this tells us actually more accurately how good this UQ model are. And as we can see here, even here, they perform the same. So not only for the approximated change, but also for the exact change. Okay, I hope that you can see here, but maybe it's not that much clear. In these figures, I have calculated, I have considered to see in each model, sorry, in this case for the Lasso model, to do the feature importance analysis. So in this case, with the orange line, we have the R squared for the test, and with the blue is the R squared for the train. And so we consider the Lasso model, and for example, we first choose here in this case, in this part A, sigma is chosen as the first most important feature, which is the volatility that we have varied. And directly after this one, important is this this gradient information that comes from the gradient with respect to Y0. And then we have other gradients with respect to some bias term and so on. So actually here we have a lot of parameters. So imagine we have 15 neural networks, and each of these neural network has 2 hidden layers, and each of them has weights and biases and so on. And let's say roughly we have like around 100 parameters here together with this gradient information. So I've just cut this in this graph here, just to show the first 5 most important features. And as you can see here, the gradient information enters, and then the last 5 least important features. And so in this first part is in the case when we have perturbed the volatility with a fixed standard deviation. Here, the Lasso works very well. But in, for example, in the case when we not vary only sigma, but we vary also other parameters, the lasso is not performing very well. So it says us, this means that for this kind of approach, we actually need to consider nonlinear uncertainty quantification models. And so slightly the same are the results when we actually consider stochastic we consider a stochastic perturbation for the volatility. And in case of the XGBoost, we see that this approach is, so the results are much better here. And we can see that directly this gradient deformation enters here in the model. And yeah, so also for case B and also for case D. Another thing that we also studied is that we wanted to see whether these models where we vary only sigma can actually generalize for other values of the parameters, because here we fix the capital T to 0.33, for example, S0 to 100 and so on. And now we wanted to see if they can actually do well even for other parameters, for other values of T, let's say, and S0. So if they can generalize better. And as you can see here, they do very well. So lambda hat here is the approximated change, and lambda is the exact change that we can calculate because we have the exact solution. And as you can see here from the results, this model also performs very well even when we vary capital T. But when you can see here, when we vary as 0, for out of the many options, it starts to perform very bad. However, I'm not showing here the results for the other model when we have the stochastic perturbation for the volatility, but the results are the same. So the same generalization. And what we can conclude from all of this part is that the gradient deformation, that this approach that we consider to quantify the uncertainty actually adds significant improvement for learning an uncertainty quantification model. Moreover, even when we do a perturbation with a non-fixed standard deviation, or with that, as I was referring as a stochastic perturbation, also even here the UQ model performs equally well. And sorry, there is a typo here because it should not be A1, but this is the the model where we vary with a fixed, where we do a fixed perturbation to the sigma and we vary only sigma. So this is just the conclusion from this slide here. And the conclusion is that it performs very well actually when we vary only sigma, but it can also perform well even in a closed domain of the parameters, as we saw in case of the maturity T. And the other A2, there is a mistake here, is when we consider a fixed perturbation to the volatility and we vary all other parameters. And this kind of model, as we actually generalizes better the quantification of uncertainty. And in this case, you can consider a European call or a put for any parameter, capital T, R, S0, and so on. Because if we go back here in the table, so in the very last, so I refer to this to this part here. You can see that the R squared by using the XGBoost in the training sample is 1. And here we vary, we solve problems by varying all the parameters. And in the testing sample, it is also very good. So this means us that this actually can generalize very well. And moreover, we also consider the option pricing with different interest rate, where we don't have the analytical solution. And just to go a little faster here, for some parameters, the perturbation is the same. The only difference is that here we don't have one interest rate, but we have two different interest rates, RB and RL. And we vary this, and we by sampling for uniformly distributed here, such that this condition holds, RL less or equal with RB, because this is an arbitrage condition. And then all other elements are the same as in the Black-Scholes case. And in this table, I have shown again the same thing by considering the baseline models and also considering these other models that also have the gradient information. And as you can see, even the results here are very well. Even in this case that we don't have the exact solution. And here we can also see directly again about the feature importance that in the x-axis that directly this gradient information enters into the model. Also here and so on. And this is when we consider the lasso as a UQ model, and this is when we consider the XGBoost as UQ model. And moreover, also here we considered about the generalization power of the problems where we vary only one parameter, sigma. And also here the results are very good when we vary capital T, but again, not that much good when we vary S0. So even in this case, we have the same results as in the Black-Scholes. And although here we have a much more complicated driver function. And to conclude this talk, so I presented a new deep learning algorithm, so to solve high-dimensional nonlinear BSDEs, such that the main motivation of this was to reconstruct and reformulate the problem such that we could avoid the local minima problem. And this we showed from the numerical results. And sorry, 1 second. And moreover, we also developed an approach to quantify uncertainty from deep learning-based methods for solving BSDEs. And some further steps would be perhaps to also consider some new algorithms. For example, here we considered the forward approach of discretizing the BSDEs. But what about considering the backward approach? Would we get some better convergence and so on? And moreover, here I showed the uncertainty quantification in one dimension, but the main motivation of applying deep learning schemes in BSDEs is to consider high dimensions. So now the idea is, what about uncertainty quantification in higher dimensions? Okay, thank you, everyone.
All right, thank you very much. Thank you.
Welcome.
I think Itamar had a question. Do you want to ask it directly?
I think you partly answered it.
Mm-hmm.
I came late to the talk, so I want to refer first to the high dimension,
Mm-hmm.
because in finance, we get high dimension very quickly, even when we look at one instrument, let alone looking at the whole market with all the instruments. Now, my question was actually, aside of admiring your thorough analysis and good methods, my question is more data-oriented.
Mm-hmm.
Namely, we have so much data in finance, and then we say the volatility is uncertain. Yes, it is uncertain. However, with data mining and machine learning, likely we can get good estimates of the volatility.
Mm-hmm. Okay.
The question is, are you aware of somebody doing such thing? Or
no. At least I am not. But we were discussing with my supervisor about what you are talking, and he told me something related to this, and which is really, really interesting. At the moment, we are not working with this part, so we are more towards this other part that we directly focus on the equations and just not too much data-driven approach. However, that is also one of our aims to work with.
okay, great. Enjoyed your talk.
Thank you.
Yeah, thank you. Any other questions? Yeah, all right. There doesn't seem to be any other questions. Yeah, thanks a lot. Thank you very much for the nice talk.
You're welcome.
Next speaker is Tatiana.
Okay.
All right. Yeah, Niga, what do you want to say?
Sorry, I have to leave now.
All right.
I think we can meet again, or we can discuss this further.
Yeah, sure. It will be nice. Yeah, sure. Yeah.
Okay, perfect. Okay, then enjoy Tatiana's talk and see you next time.
Yeah, thanks. Yeah.
Okay, so my name is Tatiana Kossaczká and I'm a first year PhD student at the Turkish University of Wuppertal. And my supervisors are Matthias Erhard and Michael Gunter. And today I will talk about deep smoothness WENO method with applications in finance. Okay, so let's start. So firstly, I'm not sure if all of you know this method. So I will just briefly introduce this method and just tell you something about this method and where this method actually comes from. So to the start, I would say this is a high order shock capturing method, which was originally designed for solving hyperbolic conservation laws. And why? The reason was that in solving of hyperbolic conservation laws, very often discontinuity shock wave or rarefaction wave may appear in the solution, and this is hard to capture. And this is actually high order method, as I said, and also with high order methods, this is even more difficult to capture these discontinuities. So what's this method based on is a measure of smoothness, and I will talk about this later. And also this is a part of my research, how to improve this measure of smoothness so that we can achieve better solution, basically in these areas of discontinuities. Later, this method was also applied on nonlinear degenerate parabolic PDEs, where also some discontinuity may appear because these degenerate parabolic PDEs, they have very similar behavior to that one of hyperbolic conservation laws. So that was the reason why also this method was generalized for this type of parabolic differential equation. So, and as I said, solving of these problems is a challenging task in most cases, and moreover with the high order methods. So this gives us enough room to improve the existing methods. And I would say to the beginning that my approach is different to that one of Lorenc, because actually I'm not searching for the solution using deep learning, but I'm just improving the existing method. And this method can be then applied to any type of PDE, I would say, but we train it separately for particular PDEs just to find the best possible solutions. So this is very important to realize that in our approach, we are developing a new numerical method. We are not just searching for one particular solution using deep learning. Okay, so as I said, we use deep learning to improve this method. And to this aim, we use the convolutional neural network. I will say later why we use exactly convolutional neural network. And what's our second goal is to preserve the consistency and convergence properties of the original WENO method, which is not so easy, or how to say, because if we add deep learning to some method, it's not like it has to converge in all cases, but we want to preserve the convergence and consistency. And we firstly applied our approach to hyperbolic conservation laws, and then we also extended it to nonlinear degenerate parabolic equations. And what's part of our current research is to apply this method also to computational finance problems, because as I said, this method is widely used in cases where strong discontinuities appear. And this may be the case of the computational finance problems, because we often have the discontinuities in initial or terminal data. So the numerical solution tends to oscillate near these discontinuities, especially when we use the high order schemes. So that's what actually motivated us to use this weighted essentially non-oscillatory method for solving of computational finance problem. This was the topic of my master thesis, and now I also want to use this deep learning based WENO method to solve these computational finance problems. Yes. Okay. So firstly, I will just briefly introduce the method, what actually is about. And as I said, this method comes from the era of hyperbolic conservation laws. So I will just explain it on a very easy example of hyperbolic conservation law. It's just this first equation here. So F is a flux function. And what we want to do firstly is to discretize this equation. So we do spatial discretization of this equation, and we get something like this. This is the discretization of flux function F. And as I said, this is higher order method. So it should hold that this derivative is approximated to the high order, namely to the fifth order. Yeah. So, and how it is made. So, as I said, it's high order method, so we have to use a wide stencil for approximation. And for approximation at grid point xi, we use 5-point stencil xi minus 2 to xi plus 2. And these points, these grid points, are used for the approximation of this numerical flux. This is the first part of this discretization. And this is done in a very similar way. But then this wide stencil is divided into 3 candidate substencils on which we construct numerical fluxes f hat and f hat m. M is from 0 to 2. And then we combine this f hat m with some weights to get the final approximation of the flux f hat. And these weights dm, they are called just linear weights. And if we would use them, we would get just the central upstream numerical scheme. But the idea of WENO is to replace these linear weights by nonlinear weights, omega m, and we use so-called smoothness indicators as a measure of smoothness of the solution on each of these 3 candidate substencils. So if in one of these substencils is some discontinuity, this smoothness indicator should tell us about this discontinuity, and that one substencil should be, in the ideal case, eliminated and not used for the final approximations. So that's the basic idea. And yeah, as I said, we want to replace these linear weights, which would form the upstream central fifth order scheme, by nonlinear weights, and we call them omega. And we do it just in this way. And as you can see, here is this linear weight dm, and it's divided by epsilon plus beta m. And this beta m is the most important parameter of the method, because this is the smoothness indicator which should actually tell us something about the discontinuity which can be present in a solution. And epsilon is just a small constant to avoid the denominator to become 0. Yeah, so we are interested in this, in enhancing of this beta m. And how these betas were actually defined, it was done in 1996 by Xiang and Xu, and they defined in this way. As you can see, here is this sum from 1 to 2, and here are some derivatives of Pm, and Pm is the approximation polynomial of a flux function on the small stencil, on the small substencil Sm. So it should tell us something about the smoothness of this approximation polynomial, because we have here some first and second derivatives. And actually these betas have an explicit form which can be easily computed. And so they were defined like this, and then they are used until now, and it works really, really good. But as I said, in some cases, it's not perfect. So that gave us actually the opportunity to enhance these betas. One idea could be to learn with deep learning these betas, but then we couldn't guarantee actually the convergence of the method, because it would be difficult for the deep learning algorithm. Actually, I would say the deep learning algorithm would have to learn to be convergent if we would want just to learn all of these betas. So what we want to do, we want, I come to the next part, we want to use these original betas, and we just multiply them with another parameter. We call this parameter delta, and doing so, we preserve the convergence and consistency of the method, because we have something on which we can rely on actually, because this is the thing which is known, and we know that with this parameter the method remains convergent. So we just multiply this beta with this parameter delta. And for example, neural network algorithm can learn to delta to be 1, for example, and then it says that, okay, WENO method is completely okay. It's fine and it remains the same. But in the cases where we want to enhance the method, neural network algorithm learns to enhance this beta so that the final numerical scheme is better in the end. And yeah, as I said, we multiply these betas with this parameter delta, and this delta is the output of neural network function. We call this function phi x, and why is here this O of delta x? I will come to that later, but we just define it like this. And very important is just to realize that these deltas are outputs of neural network, of particular neural network function. And C is just a constant, which is also important for our proof of consistency and convergence. But for example, in our research, we've chosen this C to be equal 0.1. But you could actually choose also another number, another constant. Important is that this is bigger than some kappa, and this bigger than 0, just for our proof of consistency and convergence. Okay, so that's actually the basic idea, and just to conclude what I said, and what we actually do with by improving this method, this figure says and illustrates it very fine. We have some values of flux function here, fxi minus k to fxi plus k, and we use these values as inputs to the neural network, and from these values are actually also original betas computed, but we also here we can see we use them as an input to convolutional neural network, and then the outputs of these convolutional neural network are these deltas, and we define these deltas in a way that we shift just delta, we shift this index I just by -1 or +1 just to get this O of delta x. So then this formula holds, and then we just multiply the original betas with these deltas. Then we have new smoothness indicators, and then everything remains the same. So these nonlinear weights, omegas, are computed. These flux approximations on the small substantials are computed, and then they are just multiplied to get the final approximation of on a big substantial. So you can see this is actually what's added to the original method, and that's actually how we do it. Okay, so now I will just tell you something about the idea of the proof of convergence of our new method. So as I've just written here, these two conditions, which are the sufficient conditions for the convergence of original WENO scheme. You can see it's just a condition that this is just the relationship between these nonlinear weights omega m and linear weights dm. This has to hold. And just to, I don't want to go to very much details here, but I will just tell you that it was shown that the original nonlinear weights as presented in the original paper does not fulfill these conditions in the critical points where the first derivative of flux function f vanishes. And then many improvements of WENO scheme and its nonlinear weights have been done. And we also use this improvement of the original WENO scheme. So not this one from 1996, but for this one from 2008. And they just look like this. And as I said, I don't want to go to very much detail here. We just use these new nonlinear weights because it was proven that these can guarantee us also the convergence in the critical points. But here is also this parameter beta, which we improve. Okay, so that was just something about the method. I explained it on very briefly on hyperbolic conservation laws, and analogous procedure can be found and has been used, for example, by Hajipur and Malek to modify the nonlinear weights of the WENO scheme for nonlinear degenerate parabolic equations, and they call the method WENO method. Yeah, okay. So, as I said, we use convolutional neural network to learn and predict these parameters delta. And why? Because the convolutional neural network is spatially invariant. And this is actually very important because we want our numerical scheme to be spatially invariant. And we want our multipliers, delta, to be independent of their position in the spatial grid. So that's why we also use this convolutional neural network. And the second thing is that it's also computationally efficient. And the second thing is that we use the differential activation functions, such as exponential linear unit function, L, or sigmoid. And we define the multipliers delta M such that it holds. As I said, these 0, 1, and 2, it's the index of the substantial. Yeah, so this is delta on substantial 0, this is delta on substantial 1, this is delta on substantial 2, and we see it's just a index shift here. So that's why also it holds that, as I've written here, that if we realize that neural network function f is differentiable and spatially invariant, we can write it like this. So we have f as the neural network function. These are the input values. So these are the flux function values in particular points x, grid points xi. And then we use this phi as a function composition of this big F and small f. And as I said, we use this index shift, so we can write it then such like this. This actually phi xi minus delta x, and all of these deltas can be then seen like this. It's phi xi plus all of delta x. And when we have this formulation, then it's easy for us to prove the convergence actually, because this is very favorable formulation. Yeah, so this 2k plus 1 is the size of the receptive field of the whole convolutional neural network. Yeah, so these are the inputs. And as I said, these betas M, they have explicit form, they can be computed explicitly. It means they have also Taylor expansions, and they can be also found and computed. And it's like this. So beta M is, we can see it's just all of delta x to the power of 2. And here we have these deltas in this favorable formulation, and we just multiply the original beta with our multipliers delta M, and then it's easy for us to check that the sufficient conditions for convergence are fulfilled. Yes, so also I would say our approach can be seen as a proof of concept that also deep learning can be used to improve existing numerical methods and preserve the consistency and convergence of these methods. Yes, okay, so now I will come to the application. Firstly, I will show you one example of computational finance that is just the basic Box-Holz equation, which looks like this. So I think you all know this equation. We have here some price of underlying asset at time t, which is denoted by S, some riskless interest rate and volatility. And we applied our method to the example of a digital option, because digital option is like a benchmark example where a strong jump discontinuity appears in a terminal condition. So it's the Wiener method could be seen as a method which could be used efficiently for solving of these PDE with with digital for solving of this equation for digital option. We just then transformate this equation to get forward Black-Scholes equation, where we can see we have here some parabolic term, we have here hyperbolic term and a reaction term, and for both of these terms, for parabolic term and hyperbolic term, we used the WENO method and the discretization and the WENO discretization. So yeah, this equation can be then seen like this, where f is actually identity. Yeah, we have here this or identity multiplied by this factor, and here also we can have here we have also like identity function multiplied by this factor, and then we just simply discretize these two flux functions like this. So for the parabolic term, we used WENO discretization for parabolic equations. For hyperbolic term, we used the WENO method for hyperbolic equations, and this is just a reaction term. And these these f hat and f tilde are the numerical flux functions. So this is just simple discretization. And how we proceed? So firstly, we observed that the oscillations are present basically in the first few time steps of solutions. So if we applied the original WENO method for solving of problem of linear digital options, we observed that there have been oscillation in first few time steps, and that gave us the opportunity to enhance the solution using deep learning, and we want to actually to get rid of these oscillations. So we define our loss function as I called it test of monotonicity, because here this is some number if the oscillation is present. If there are no oscillation, it's just 0, and we just sum all of these values. This is the one thing, how we define loss function, and we also pre-process the solution from the last time step. And for this, we use these values of flux functions in grid points xi plus 1 and xi minus 1. And we use just first and second differences as input values to the first hidden layer. And what I would like to say as well is that our neural network is rather small, just to save the time, because we don't want to use some big neural network. We just also really use very small or rather small neural network, just to be computationally efficient. So there are just these two input layer, then one more hidden layer, and then output layer. And here in between are some activation functions. As I said, I use differential activation functions, which also guarantees us the convergence. Yes. So, and how we proceed in the training. So we want to solve the Black-Scholes equation for digital option, and our aim would be to solve it to many different problems of digital option, also for different sigmas and also for different R. So we pre-generate these parameters randomly. We fix strike price and also the time, terminal time equal 1. And in training, we proceed as follows. We initialize the weights of convolution neural network randomly, and we do one single time step of a solution, because as I said, these oscillations in the solution are present basically all in the first few time steps. So we just show the neural network the first time step of solution. After that, we compute loss, do gradient update, and test the model, and then repeat the above steps. And by repeating the above steps, I mean that we pick another sigma and another R. So we show the neural network many different problems, so it can learn to generalize very well. And then we choose the best performing model as final model. And here we stop, and we say this is our enhanced numerical scheme, which can be then used for any type of parabolic equation with any type of parameters. And here I will show you just two examples how it works. For example, if you have digital option and this is the terminal condition, so here is a strong discontinuity, and using standard WENO method, you can see there are some oscillations, but using our enhanced method, we called it WENO-DS, we can get rid of these oscillations. So you can see here, they are not anymore, and these parameters, they were just randomly generated. And in most of the cases, the standard WENO method is able to capture these oscillations well. And for example, in terminal time, if we fix it t=1, it is able to get rid of these oscillations. But in some cases, even in the terminal time, the oscillations of the original WENO method are present. And if we use our enhanced method, they are not there anymore. So this is a big advantage of this method, I would say. And here in this table, you can see that we actually do not exchange these oscillations with error, and our method also produces smaller error. Here are just some randomly generated parameters, and we see that in all cases, the error in the terminal time t=1 is smaller than the error of the original method. And to the end, just to demonstrate that the method remains convergent, namely high order convergence, we tested this new method, this WENO-DS method, on a transport equation with continuous initial condition. And as you can see, we have here fifth order of convergence, as already has been analytically proven. And what's also important to say that we do not retrain the neural network in this case for different ends. So just how we trained it on this data of digital option, we just took this method and applied it to the transport equation, and as you can see, it remains convergent. And we also applied it to heat equation with continuous initial condition, and here we should have order of 6, and as you can see, it's also preserved here. Yeah, so here we also did not retrain the neural network, but we would recommend for more complicated equations to retrain the neural network for different partial differential equations, just to be sure that really our method is the best performing for this particular PDE. Yes, so this was the example of computational finance. And now, just to show you very briefly, what was the part of our piloting research is actually the application to the hyperbolic conservation laws, because this is actually the area where this method comes from. And one of the benchmark problems is the Buckley-Leverett equation. And I will just show on this example another training procedure or another ideas for loss functions. Maybe this is interesting for some of you. So we have here some hyperbolic conservation law with this nonlinear flux function. And this flux function has here some parameter A. And according to this parameter A, we can have many different hyperbolic conservation laws here. So we decided to generate this parameter A and then produce actually more hyperbolic conservation laws, and then find the appropriate numerical scheme for solving of this equation. And as you can see, here is some initial condition which is discontinuous. So here is also strong jump, and the original WENO method also produces some oscillation, even oscillations, or some yeah, it's not perfect. That doesn't work perfect. So that also give us this opportunity to improve the method. So we construct loss function in different way compared to the example of computational finance. We defined it like we add just mean square error loss with I've called it overflows loss, because we know from the behavior of the solution that it should be between 0 and 1, and we just want to check if this solution is always between 0 and 1. So this is this overflows loss that, and it is some value if the value of the function of the solution is above 1 or underneath 0. And this is just mean square error, where here we have some reference solution, which we had to compute before. So how we proceed in training? Firstly, we create a data set for which we compute the reference solution on fine grid, and we choose A randomly from this interval. And in training, we choose randomly one reference solution from a data set. And then we initialize the weights of convolutional neural network randomly and go through the whole solution up to time t. And after each of time step, the gradient update is made, and the model is tested. Yeah, we tested it after the last time step of a particular problem with a randomly chosen A. And then again, we choose the best performing model as our final model. And this is the numerical scheme, which is then used for any parameter A and for solving of this Buckley-Leverett equation. And this is how the loss, on this picture is actually the progress of loss value shown. And we can see there are like two patterns. These are the lines for different parameters of A, and I would say we have chosen the model somewhere from here as the final model, because then we see that the neural network starts to overfit for some parameters of A, and it doesn't make any sense to train it further. So we would stop here somewhere between 40 and 50, and we choose the model from here as the final model, and then we use it for solving of the Buckley-Leverett equation. And here are just some illustrations, and you can see that our method really performs better, especially in these areas of discontinuities. is able to better capture the shocks. And if you look on the error, we can see that WENO-DF is our method. We can see that it's smaller in almost all of the cases. In this one case, it's bigger, but this may be caused just by the fact that maybe somewhere here would be some line. This is a validation set, it's important to say. Maybe somewhere here could be also some line where it starts to increase somewhere, like here, for example, after 30. Yeah, so here is just one small increase of error, but in all other cases, we can see that our method performs better. And here is the biggest improvement for this parameter A. It's even 2.3 times smaller error using our method. Yes, and this was one training procedure. Then we also tried another training procedure, and this was the part of our second paper, where we generalized the methods for nonlinear degenerate parabolic equations. And here we, after choosing a problem from dataset, we did not go through the whole solution, but we just did one time step and then used the CNN to predict the multipliers of the smoothness indicators. And then with pre-specified probability, we opened a new problem from a dataset, or we continued with another time step of a problem uniformly sent from the set of already opened problems. So this actually mixed the problems, and it's just another approach, but the results are very, very similar. But this training procedure is even more effective, and we applied it to this example. It's Bakry-Levert equation, but also with this parabolic term. And here are also some parameters A and G, which can be generated randomly. And that is also what we did. It means that in the end, we have some new numerical scheme which can be reliably used for solving of this Bakry-Levert equation. And yeah. Here is also the progress of loss function. You can see it's similar to the one of hyperbolic conservation laws, but here could be one optimal, and maybe another is here and another one somewhere here. And if we would zoom in this area, we would say that there is a small decrease in this area, but then it starts to increase rapidly. So there could be another optimal for another set of parameters A and G. But we just took the model somewhere from here and used this numerical scheme as our final numerical scheme. And with this method, also improvements can be achieved. Here is just one example with some specific initial condition of this Bakry-Levert equation. We can see that our method here captures the discontinuity better. And also if we look on errors, we can see that our methods for some randomly generated these are the parameters from our test set. We can see that our method produces small error in almost all of the cases. Yes. So, yeah, so that's actually all from the numerical results. To the end, I will just conclude what I have done. We applied the convolutional neural network to classical WENO methods, And we see that this leads to better results. We are able to capture the discontinuities in better way. And our method remains consistent and convergent, which has been analytically proven. We do not need any post-processing steps. Output of neural network algorithm can be directly applied to the scheme. And this CNN is rather small. It's not like any big structure. It's just really easy to apply. And we demonstrated our improvements on numerical examples in hyperbolic conservation laws, nonlinear degenerate parabolic equations, and the examples of computational finance. Okay, so that's actually everything from my side. Thank you for your attention.
All right, thank you very much. Thank you. Any questions? Yes, no question. Yeah, just maybe like as I mentioned, like maybe worth like seeing what reservoir computing is does, because apparently there's a lot of applications from reservoir computing to finance. I don't know how these kind of approaches would help. So apparently you can also reduce the computation costs, etc. So maybe worth comparing to this. I don't know.
One more time.
No, I just said it may be worth comparing to approaches like reservoir computing,
Okay.
and see, yeah. I mean, again, this is not my field. Like the finance stuff is not my thing, but yeah. I mean, I heard like previous talk by Joseph Teichmann about yeah, reservoir computing for finance, and apparently they are doing quite well. So it may be worth comparing to see yeah, what approaches. Yeah. Yeah, all right. It seems there are no other questions. All right, then. Yeah, thank you very much, Tatiana, and thanks again to both of you for this nice thematic afternoon about machine learning and numerical systems for finance. Yeah, thanks a lot. Thank you. Okay, take care, everyone. Bye-bye.
Thank you.